This might be the coolest thing we do in this entire course. We are going to build an actual working search algorithm for a piece of Wikipedia using Apache Spark and MLlib, and we're going to do it all in less than 50 lines of code. Pretty awesome. So let's go ahead and open this up in Spyder or whatever text editor you want to use, really. And we'll go to our course materials folder and open up the tfidf.py script. And let's talk about this. And here we have it. Now, step back for a moment and let it sink in that we're actually creating a working search algorithm along with a few examples of using it in less than 50 lines of code here. And it's scalable. I could run this on a cluster. It's kind of amazing. All right, so let's walk through this. It's actually fairly straightforward. All right, we're going to start by importing the Spark Conf and Spark Context libraries that we need for any Spark script that we run in Python. And then we're going to import hashing TF and IDF. So this is what computes the term frequencies and inverse document frequencies within our documents. We'll start off with our boilerplate Spark stuff that creates a local Spark configuration and a Spark context created from that, from which we can then create our initial RDD. So we're going to use Spark context to create an RDD from subset-small.tsv. So this is tab separated values, and it represents a small sample of Wikipedia articles. So that gives me back a RDD where every document is in each line of the RDD. So this TSV file contains one entire Wikipedia document on every line. And I know that each one of those documents is split up into tabular fields that have various bits of metadata about each article. So the next thing I'm going to do is split those up. So I'm going to split up each document based on their tab delimiters into a Python list and create a new fields RDD that instead of raw input data now contains Python lists of each field in that input data. And finally, look at what's going on here. So now I'm going to map that data, take in each list of fields, extract field number 3, which I happen to know is the body of the article itself, the actual article text. And I'm in turn going to split that based on spaces. So what this does is extract the body of the text from each Wikipedia article and splits it up into a list of words. Okay, so my new documents RDD has one entry for every document, and every entry in that RDD contains a list of words that appear in that document. Now, so we actually know what to call these documents later on when we're evaluating the results. I'm also going to create a new RDD that stores the document names, and all that does is take that same fields RDD and uses this map function to extract the document name, which I happen to know is in field number 1. So I have two RDDs, documents, which contains lists of words that appear in each document, and document names, which contains the name of each document. And I know these are in the same order, so I can actually combine these together later on to look up the name for a given document. Now the magic happens. So first thing we're going to do is create a hashing TF object, and we're going to pass in a parameter of 100,000. This means that I am going to hash every word into one of 100,000 numerical values. So instead of representing words internally as strings, which is very inefficient, it's going to try to, as evenly as possible, distribute each word to a unique hash value. And I'm giving it up to 100,000 hash values to choose from. So basically this is mapping words to numbers at the end of the day. Okay, and now I'm going to call transform on hashing TF with my actual RDD of documents. So what that's going to do is take my list of words in every document and convert it to a list of hash values, a list of numbers that represent each word instead. Okay? And this is actually represented as a sparse vector at this point to save even more space. So not only have we converted all of our words to numbers, but we've also stripped out any missing data. So in the event that a word does not appear in a document, we are not storing the fact that that word does not appear explicitly. It saves even more space. Now to actually compute the TF-IDF score for each word in each document, we first cache this TF-RDD, because we know we're going to use it more than once. And we use IDF with a min doc frequency of 2, meaning that we're going to ignore any word that doesn't appear at least twice, call fit on TF, and then transform that on TF. And what we end up with here is an RDD of the TF-IDF score for each word in each document. Okay? So let's try and put that to use. Let's try to look up the best article for the word Gettysburg. If you're not familiar with U.S. history, that's where Abraham Lincoln gave a famous speech. So we can transform the word Gettysburg into its hash value. Okay, that's what this bit of code does. We will then extract the TF-IDF score for that hash value into a new RDD for each document. So what this does is extract the TF-IDF score for Gettysburg from the hash value that maps to for every document and stores that in this Gettysburg relevance RDD. We then combine that with the document name so we can see the results and print out the answer. So let's go run that and see what happens. Okay, so to run this, we need to bring up another Anaconda prompt. And we will cd to where our course materials are. And just type in spark-submit tfidf.py. And let's let this chug away. So yeah, right now it's actually going to be analyzing a subset of Wikipedia data, and it's going to try to find the best document match for the search term Gettysburg. And it's already coming up with an answer, and it's done already. And the answer is Abraham Lincoln. It actually worked, guys. That's awesome. So yeah, I mean, TF-IDF in action there. We actually created our own little mini search engine here with, less than 50 lines of code. Most of those are comments, mind you. I mean, the actual code itself was like maybe 20 lines. And with just that little bit of code, MLlib is so powerful, it was able to construct an entire search engine that could figure out that the article for Abraham Lincoln is the best match for someone looking for information about Gettysburg, at least in the subset of Wikipedia that we gave it. I think that's kind of awesome. So, yeah, I mean, and what's even cooler is that if I had the entire corpus of Wikipedia, I could, with very few modifications, run the same exact script on a cluster and get back results over the entire Wikipedia data set. It's scalable to that extent. So pretty cool stuff. TF-IDF in action in Spark. And we actually made our own little search engine really easily. That's awesome. And there you have it, an actual working search algorithm for a little piece of Wikipedia using Spark and MLlib and TF-IDF. And the beauty is we could actually scale that up to all of Wikipedia if we wanted to, if we had a cluster large enough to run it. Now, we've just touched on some of the capabilities of Apache Spark. I'm sure you have a lot of questions. There's much, much more to it. In fact, I have a whole course on Apache Spark, so there's a lot we can talk about. If you do want to learn more about Apache Spark, skip to the final couple of lectures in this course where we talk about where to learn more, where to go next, and there's some jumping off places there for you to go explore and learn more about Spark because it is a big topic. But hopefully we got your interest up there in Spark, and you can see how it can be applied to solve what can be pretty complicated machine learning problems in a distributed manner. So it's a very important tool, and I want to make sure you don't get through this course on data science without at least knowing the concepts of how Spark can be applied to big data problems. So when you need to move beyond what one computer can do, remember Spark is at your disposal.